It's an amount of value decreases over time, and again, it's a fixed rate. So it's going to decrease at a designated percentage or a designated rate of change. But it's exponential. It's not just take off 1%, take off 1%. It's going to be exponential. Right? So our exponent is going to be a variable. Yesterday we had a basic formula for interest. We are going to have a basic formula for decay. Or we can sometimes call it decrease. Decay sometimes is a little morbid, right? And the basic decay or the basic decrease formula is almost exactly the same as the basic interest formula. Y equals A parentheses the number 1, but instead of adding the rate, we're going to subtract. You guys are so smart. To the power of t. Right? So we have A parentheses 1, and that 1 stands for 100%, right? We always go back to that initial value of 100%. If it's $1,000, we're always working with that $1,000 at the beginning. That's what that 1 represents. And then we're going to subtract the percentage rate, right? The rate of decay. And then it's going to be to the power of t. So y is my answer. How many of you noticed there were 2 problems on your homework last night that did not have labels of dollars?
Me.
There were 2 problems that talked about people.
Yeah.
And people are still going to put dollars, right? Make sure you read. Don't just assume that it's always going to be money, right? Y is your answer. Maybe it is dollars. But if it's people, right? Just checking. A is your amount. Your initial amount, your starting value. R is your rate. And T is your time. So again, Y is your answer, A is your amount, R is your rate, T is your time. The formula is Y equals A parentheses 1 minus R close parentheses T. Now what's the problem with that variable R? What do you think people are going to forget? To turn it into a decimal. Right? But Mrs. Long, what if it says 3.5%? That's already a decimal, right? So don't I just put 3.5? It's a decimal. You said turn it into a decimal.
You silly goose.
You silly goose.
You have to take the percent and change it to its decimal equivalent. Correct? Percent means out of how many? 100. So 3.5, 3.5%, 0.035. Yes?
Oh, yes.
Okay. Here's our first example. The population decreases 1% each year. In 2000, the population of this town was 13,000. So in this one population, every year they have statistically seen that the population is decreasing about 1% each year. People are moving or dying. Not as many people are moving in. Yada, yada, yada. How many will there be in 2042. Gonna update this problem a little bit for you because obviously 2000 was quite a while ago. So we're going to predict a ways in the future, correct? Okay.
Is it like increasing though?
Now the population of the world is increasing, yes, but this is of one specific small town. This town is decreasing over time. So let's rewrite the formula because we love to rewrite it. Y equals A, my initial value, 1 minus R to the power of T. Do you agree?
Yes.
Let's substitute. Y equals, what's my initial value A?
13,000.
13,000. Then I put my parentheses. I do 1 because that's my 100%. But I'm subtracting, what's my rate of decrease?
1%.
Do I put 1?
No.
I put 1%, which is 0.01. To the power of what? This is sometimes the difficult part
42.
with decrease. You have to then sometimes calculate the decrease, right? Don't just be like, oh, 2042.
I got the answer.
Just because there are numbers in the problem does not mean those numbers are specifically used in that way, right?
Yes.
Sometimes you have to do a little thinking.
I got the answer.
All right, Malachi got an answer. What is it?
8,524 people.
Do you guys agree with that? Who else did it in their calculator?
I got 8,523.
Yeah, but
Yeah, that's what I got.
You can't have.
All right, so 8 in the calculator it says what? 8.
No.
Hold on. 8, 5, 2, 3 point 57 ... right? All right. So this is 8,523 and a half or 0.6 people.
Yeah.
We're going to use actual, right? Like if I was going to get a bus, a school bus, right? And I said, oh, if I order 10 buses, it's going to fit this many people. I have to round people up, correct? Oh my God. Zip it. People. Not dollars.
No.
Right, we're going to use actual rounding rules that help us. But, you know, like if you say like, oh, you know, fire code says that this room can have this many people in it. You can't have 0.2 of a people, right?
Cool.
All right, so questions on basic decrease.
It's next compound.
It is not compound. Decrease. I like your intuiting, though. I'm going to highlight this, just maybe that'll help some people visualize it while they're doing their homework.
Now it's yellow.
It's a new highlighter. It's a Sharpie highlighter.
That's why it's so green.
Smear guard.
No smears here.
Be jealous.
Yeah, very jealous. None smears.
All right, so the second equation is called half-life.
What's up with this whole life thing? Decay, life, like.
So here's the interesting thing. Half-life
Sound like a bee.
isn't necessarily talking about like life as you and I know it. It's talking about existence of something. So half-life, if you become a pharmacist, you will study a lot about half-life. Archaeologists study half-life. So recently they found the remains of a prehistoric teenager in a cave outside of Greece,
That's
right?
Wow.
Outside of a town in Greece. So they use this thing called carbon dating
Yeah.
Oh yeah, that's yellow.
to see when this body was from. And so carbon dating, because inside of our bodies, inside of all living things, is the element carbon. And carbon decays over time. And so they can measure how much carbon is in this body and then use a mathematical formula to figure out how long it's been around, because carbon will split in half this many times during a period of time. Medicine, if you become a pharmacist, when you take an antibiotic or when you take a steroid or when you take any type of medicine, your body, the chemicals react inside of your body and they, over time, are filtered out.
Yeah.
So you have to study this, and like doctors have to do all of these, I mean, they have calculators that do that for them, but they have to, take your weight and your age and all of these factors to see how fast your body will get rid of a certain type of medicine, because if you have too much of it, it could be a problem, or if you have too little of it, it could be a problem, right? So this half-life idea is not necessarily life as in I am alive right now and not dead, it's existence. So half-life is used to predict the rate of decay in a substance. So like the most common or the easiest, the simplest, the most basic thing that we're going to talk about with half-life, there are these elements out there that are highly volatile, right? That if you get them out and you expose them to the element, the world, they will over time start to disappear. Right? So they will slowly start to release their electrons and protons and neutrons and slowly get smaller, right?
Yeah.
So here's our formula. Half-life formula is Y equals, and we say P again for principal, or the initial amount. Where do you think this 0.5 comes from?
Half.
Yeah, half. To the power of t.
That's easy. I can remember that one easy.
Because every time one of these cycles happens, half of it disappears. And so if you think about it, like if we were talking about carbon, like if we were using this for carbon dating, right? Let's say right now I have 100. Let's make it easy. And the half-life is every minute. Every minute, half of it disappears. Right? So 1 minute from right now I have 100. 1 minute from now I'd have. Then 1 minute from then I'd have. Then 1 minute from then I'd have 12 and a half. Right? It splits in half every cycle. Now the cycles are different for each element. Right? But the trick is, these scientists, when they're dealing with cavemen, when they're dealing with bodies that they find, right, like ancient prehistoric mummies or things like that, when they are discovering that, the traces are so small because it will never leave. It will never be zero, correct? You're always dividing it in half, so half of it always remains behind, but you're just getting smaller and smaller and smaller to these minute numbers. And then those doctors have these minute numbers that they're working backwards from. All right, so here's our example. Something that I'm sure all of you have been waiting your whole life to understand this idea.
Yes.
Fluorine 20, everybody's favorite element. Fluorine 20 has a half-life, an element, a very volatile element, of 11 seconds. Meaning every 11 seconds, half of it disappears.
Wow.
Fluorine 20 has a half-life of 11 seconds. Find the amount left of a 40-gram sample in 2.2 minutes. Now here's the tricky part of this, right? We talked about it. This part, decay, exponential decay, has a little twist to it that growth didn't have. The twist is lots of people are going to try to use this value of 20. Just because it's a number and a bunch of words. So lots of elements have numbers in their name.
Yeah.
Do not get confused by the name of the substance. Okay? The second part that you need to ask yourself when you do these, do you need to convert time? Because the half-life of fluorine 20 is 11 seconds. But it's asking me to figure out an answer in minutes. So I have to figure out how many 11 seconds are there
12.
in 2.5 minutes. I have to figure out my t. I have to figure out my t value. I have to say to myself, okay, the half-life and answer time must match. Right? I've got seconds and I've got minutes. They need to match. So can you convert 2.2 minutes to seconds? 2.2 minutes
132 seconds.
equals how many seconds?
132.
132 seconds. And you just did that by what?
Multiplying 2.2 times 60.
Correct. And once you have 132 seconds, can you figure out how many t values
Yeah.
are in there?
You divide it by 11, that gives you 12.
Then I'm going to divide that by 11 seconds. So my t is 12. Again, you have to take your end value. It's asking you for 2.2 minutes. I converted that to seconds because that was what I was working with. So I did 2.2 times 60 to get 132 seconds. And then I know that a half-life is 11 seconds. So how many half-life cycles are in that 132 seconds? Well, 132 divided by 11 is 12. There are 12 cycles in that amount of time that I'm testing. So now I can use my formula. Y equals P times 1/2, 0.5, to the power of T. What does P stand for?
Principal.
Principal. Where did the 0.5 come from?
Half.
Half. And where did the T come from? What does that mean?
Time.
Time. Now again, you have to be really careful. We don't put 2.2 in for time.
No.
We have to figure out how many half-lives am I trying to find. There are 11 or 12 half-life cycles because it's 11 seconds. My total is 2.5 minutes, so 2.5 minutes is really 132 seconds divided by 11 because that's one cycle. There are 12 cycles in it. Y equals P, what's my principal? How many do I start with?
40.
40. Times 1/2 to the power of 12. Ladies and gentlemen, how come I didn't use the number 20? Where does that go in my problem?
Fluorine 20.
Nora,
Nowhere.
it's the name, right?
Yeah.
This is a really easy problem to screw up because there are 1, 2, 3, 4 numbers in the problem. Do you agree? There are 4 numbers in my initial problem, and I only use one of the numbers in my formula because you have to do some math to figure out the other one. How much is left of this 40 grams? A gram is about a paper clip, so 40 paper clips worth of fluorine 20 in 2.2 minutes. Ariana, how much is left? 0.0 what? 10? Do I need that extra 0?
No.
Is there anything after the 0 right there?
Yeah, it's 0.0097656.
Okay, hold on. Point, if I start 0.0, what?
0.097.
Got it.
5625.
0.009765625. Yes?
Yes.
And I'm going to round that approximately to the nearest hundredth. 0.01. If it is less than, let's say, 6 digits, put all 6 digits. Does that make sense?
Is that 6 digits?
Maybe let's do 5. 5 digits.
That's a lot of digits.
You'll be okay.
Wait, what's the answer?
So, I started out with 40 paper clips. Yes?
Yeah.
In 2.5 minutes, this is how many paper clips I have left.
Ooh, dang.
Not a lot, right? But is it still there?
Yeah.
Okay.